Are you guys staying or? I don't know, like, the rest of me wants to leave, but then part of me is like, if I leave, what am I gonna do at home? Like, I guess I could get started.
I just don't want to watch it.
It's like, I guess I could get started on 340 homework, but at the same time, it's like, I'm just gonna leave that.
Bro, 340 homework is.
You can do whatever, you know?
I think they were different.
It's gonna be terrible because next semester, are you doing 440 right now?
Hell no, I'm not
Okay.
doing it. I'm not doing it.
Guess what? Next semester, Ivana's not teaching it.
Yeah.
So it's like,
or you double cooked.
yeah. I mean, so are you. I mean,
Oh,
well, you actually probably learned a little bit. Huh? No.
Oh, you said 440 is not.
Got a lot of power today.
I thought you'd be taking it this semester.
No, because nothing before 80 conflicts and then let me do it. So,
The times conflict.
yeah, now I'm taking another elective. Honestly, it's better because like other electives, like we're learning a lot.
And electives are like usually the higher cost. It's better just to get them out of the way now while you can.
Well, electives are good. Very easy. They're actually help.
It's like, why don't they, do that with actual classes that you need? I don't know how, right?
Read out. I guess.
Okay, so, just a few things, I think if you're here, you know it, if you're not here, you're listening to recording. A couple of things you pay attention to, our project already posted. You pay two of them went still shown, the other one still in April 20th. So those are simulation based. We're not gonna do any demo in class because we assume that you already know how to use like a spice, PSpice or IoT spice. But just follow the step, do the simulation and then copy the result, and write your report. So it's a fairly simple practice. So that's one thing. Another thing is that, as our quiz for next week, it's gonna be what's covered today. So, so from now on, I'm not gonna reply to email saying, oh, what is gonna be covered in the quiz? So you know, it's covered in class, it's in the quiz, it's on the quiz. Not covered in class, it's not on the quiz, okay? The quiz is 100% based on the lecture today. So next week is based 100% based on lecture today. So I know that some students don't come to lectures and don't watch the video and simply don't do anything. They're asking me, what is this, what is that, what is that? And it's not fair for me. I mean, you don't respect my work. I mean, it's just, I feel pretty, pretty sad and I feel uncomfortable, when people say, okay. But anyway, so I think, you'll see some quizzes are gonna be easier and more difficult because I have my TA already practiced it. It seems to be okay, but sometimes, he could have a different background, so sometimes could be easier, but I think, so far, it's pretty well. The quizzes we are seeing, if I take all the zeros, we'll average roughly 75% or more, which is pretty good. And taking moving on, we drop a few, and then you have final exam, and you have projects basically give away, and you have homework basically give away points. So you add all together, a lot of you are gonna get A's if you do your hard work. So that's what it is. I mean, if you don't do your work, there's really not much I can help. This class is very difficult class, I understand, because we got a lot of equations. And I've been keep saying that like chapter 8 is the most difficult one because if you look at a circuit like this, you might say, what is it? Well, if you cut this in half, it's exactly what we are covered in chapter 8. Chapter 8 we covered already. And we're not going back to redo what we have done in chapter 8, right? So that's sometimes we start to write down some solutions. And if you forget what you have learned, you say, oh, what are you doing? Well, you learned a couple of weeks ago, right? So that's, so you really have to, I mean, you're here, that's great, I appreciate it, I really appreciate it. But if you're not here, you got to watch the videos. You got to know what's covered, what's not covered. And we're gonna skip some of the content. If the book is too thick, we just cannot cover everything I wanted to. So we'll be skipping something. For the ones that are skipped, if you have time, read them. It's good for you. But if you don't have time, okay, fine. Because we're not gonna test them, right? So, but those are the only ways. Attending lectures, read the book, doing the homework, and especially the homework. answers given. So you got, and a lot of the homework are very similar to the examples. And moving on, you'll see that more and more often our quizzes, problems, very similar to the either the problems, either the examples or the problems you have done in your homework. So it's no surprise. Okay, it's always that way. And even when you come to the final, it's going to be very similar too. We're not going to make up something that you never learned. It's going to be something you look at, you say, oh, this is something that I've done before. If you haven't done it, you know that you have done it. It's similar, okay? But if you have not done it, of course, you're going to get lost because by the end of this class, you're going to see, oh my God, so many equations. To be honest with you, myself, I cannot remember all the equations. No way. There's no way I can remember. But my way of is I know where to find it, and I know the approaches how to solve the problem, and technology is developing so fast. When I was in college, we didn't have this class. When I start teaching the class, I have to learn myself. Okay, so you guys, move on. If you stay in electronics, and this is probably the most important class, 330, 340, 330, 430, those are most important basic class. You're gonna come back again and again to look for the competence that you need, for the skills you need for your job. But of course, you move on to something else, that's a different story. But this sets the foundation. So this is really good stuff, right? So today we're going to try to finish up chapter 9. This we already talked a little bit last week, but I just want to quickly go through a few slides to recap. Like this, if you look at this circuit, you start to realize that this is the differential amplifier. Like at the bottom, you have inputs, and you have an input, you have common mode input, and you have differential input. Now, one of the things you look at for the differential input, it has to be positive up here and the negative up here. So why is it positive in second? Can we put a plus sign here? Or if you put a plus sign here, it becomes common mode because they're going to be the same. If they're the same, they're called common mode. If they're different, they're called differential mode. And in small signal models, you can always do separate. You can always do separate superpositions, which means we can do the problem by applying theorem only, we get the one answer, and then we apply the differential input, we get another answer. We add them together, we get the final answer. Of course, you know that for common mode input, the output is 0 because this output is going to be identical over here. But for differential input, you get the opposite output. You get positive output here, negative output here. Then you use this one minus this one. You got the gain. Well, the gain is very the same as a single stage amplifier or single ending. The reason is that because the input is only half, right? So the gain, each of them is half. You add them together, you got 100% gain. But and then what can you say? What's up there? Well, if you look at out there, these two Qs, here Q4, they form a current source for this amplifier. You say, well, the current source looks a little bit different because previously the current source always have its gate and source connected, but this one is not connected, right? Our drain is, drain and gate connected, but this pin of the drain here is not connected. Well, the reason it's not connected because these are the actual load current. You must have another device here to provide the reference current. The reference current is going to be actually connected. So if I add something here, you can add another transistor right over here. It will really help you to understand. And this one here got to be connected. So it's going to be like this. And over here, you might have some sort of high reference coming in. Right? So this is how you interpret. And then this becomes the current source, but that's the reference current coming in. And then you will say, okay, great. And then what are these two are going to do? Well, first of all, it provides the reference current you need. Now you might say, oh, I already have reference current here. Do I need one here? No, actually, you don't actually need one here because you already have one here. But all this one here is to replace the resistor we had on the previous like pictures that we had a resistance load. Again, time and again, we say we don't want to use resistance as a load. So you have to have a load. So what do? We replace it with them with a current mirror or current source. And the current source is a DC current in parallel with a small signal resistance. And this is RO, this is like an early resistance. And for small signal, this DC current, constant current is an open circuit. So therefore, you come up to be add only a resistance as a load, which this resistance is the internal resistance of the MOSFET. It's not an external resistance. That's why you do this, and it helps you to build this integrated circuits. Right, so this is your small signal model, and if you count this one, this is your load resistance, and you can get the gain right away. And then here, apparently for small signal, this is virtual ground because it current flow because this will then go here. So that's as simple. So moving on, that we can do the BJTs. Pair is very similar. I think we talked about this also last week. You got two BJTs back to back. And you got, again, look at it carefully. We got a resistance and a load. And this resistance, of course, also does the biasing as well. You have a current here to the biasing, but you have another one. And the current circuit is very simple, very the same, except that the input voltage is applied to R-pi. But for MOSFET, it's applied to open circuit. So that's the only difference. So the result is a little bit different, a little bit more difficult, complex, but eventually you draw the pi model of each one, and you get the gain, and you get the voltage gain, which is going to be very, very similar. So here we have two examples. One is applying VCM on both input, and you can see that when you apply VCM on both input, the output is identical, right? So that's why this output is 0. So that's called common mode output is 0. And then this one shows that if you ground one there, you apply voltage here, so that's a differential. That's not a common mode anymore, because even though it looks like DC, but it's not common mode because they're different. But when you apply one mode here, you have a problem, because if you look at it here, you assume this both of them in the active mode. We're in a little bit of trouble, because let's say if this is on. If this is on, this is 1 volt, and this voltage drop is 0.7, so we got here will be 0.3. And if this is 0.3 and this is ground, you see what happened? This is higher than ground. So this got to be off, which assumption is correct. But if you start by assuming this one is on, this is cut off, you will be redoing the job, because if you assume this is on, this is 0, this will be minus 0.7. If this is minus 0.7 and this is 1, so the difference will be 1.7. That's no good. You cannot have 1.7. It got to be 0.7. So what it is tell you, your common mode, the differential mode, the voltage cannot be too big. If it's too big, one of them is going off the linear mode. It's no longer an amplifier. So the input voltage between these two in differential mode has to be very small. That's how you also identify the common mode range for this BJTs. So we're gonna skip that. And here you see we did this one, but now we look at this one. If we put a small signal here, so look at the ground, which is okay because this is so small. Even though the current induced here is slightly different, but overall the DC is still 0.7 volt. And only difference that the current is going to increase a little bit, but this current is going to decrease a little bit, right? So the total current is like this, and together you got I over here. So therefore you get voltage here and voltage here, and you look at the difference. That's your output is 2 alpha times delta I times IC. So that delta I is because of the small signal. So that's how we get the gain of this. I think we did this example last week, so probably going to skip that. And you can use a pi model, but you can also use a T model. Sometimes it's easier. In this case, for example, if you use a pi model, you can find the gain and all the things that you can do. But if you use T model, you find it's a little bit easier because you can find the voltage across this and across this, right? And then you can find the voltage on here. So what this does is that if you look at, for example, let's look at the voltage VID, and you can find what a VID is. It's going to be the current. VID is plus here, minus here, so it's over here. So it's going to be current IE times 2 times RE. You got VID as the input. So this and plot this current going this way, so two resistors times current, you get voltage here. And then for voltage over here, we got VO1. VO1 is going this way, so it's going to be IC times RC. And VO2 is going to be minus IC times RC. So, and then we know that IC is beta times IB, and then we know IE is equal to IC plus IB. Yeah, it's consistent. Maybe this should be using this IB. Right? So you plug in all these equations here, you get the voltage. Now then you get a gain. Your gain is going to be VO1 minus VO2 divided by VID. So you do this, you don't have to find what exactly like the current is going to be, because current is going to cancel. So that's why it's very easy to get the gain for the if you use this T model. But then of course if you have sometimes surprisingly you have resistance at the emitter, and this is very common because you have like a current sources, and sometimes you have some other needs, like you have resistance here. So if you have resistance here, the equivalent circuit for T model is going to be exactly the same, except that now you have RE is lowercase plus capital RE, right? So now you can get your gain. It's fairly simple, like the previous one you had. Now you have VID equal to IE times 2 times RE plus 2 times RE. And then your VO is going to be the same. So your gain is going to be VO1 minus VO2 divided by VID. You got your differential gain right away. Again, you don't have to actually solve for the current, exactly current amount, because the current eventually are going to cancel themselves in the equation. And this is very much used later on. Your last example in the book, the very, very last part of the book, it tells you how to look at the ratio between different currents so that you cancel the current and you get the gain. You don't have to solve the circuit. But of course you can solve the circuit and you'll get more insight. Like, okay, what is the current? What is the actual current? That helps. But if you just want to know the gain, you don't have to go to details of calculating the circuit. So this is what we have. And also I want to come back saying, some students say, well, you got RE here. What's the difference between RE here and RE here? Well, if RE is here, in the equivalent circuit, this is the ground. Why? Because there's no current going, the small signal current going between this. The small current going between this one, this is only DC, and the lowercase current go that way. So if only current DC, therefore, we basically get rid of this for small signal, and both of them is like a connect to ground. So I mean they're virtual, but they actually not a ground, but they look like a ground. So that's why when you solve for this, you can assume this is the ground. But again, they are only virtual ground, they are not actual ground, but they're connected. If you separate them, make it easier, because if you separate this two, you get, instead of adding this together, you basically have two amplifiers. You got two amplifiers, one amplifier here with positive input, and another amplifier with negative input, and you can get the gain of each amplifier. You use this one minus this one, boom, you get the output voltage. Now you get the gain. So in this case, your gain is yeah, it's very easy to calculate if you again use the previous page, use the T model and so on, right? So this is again, this is equivalent circuit of the half circuit. So this is like any one of them, either this one or this one, and you get a half circuit. And we draw the equivalent circuit with the pi model. You know, input one half, that's the positive half, right? That's the base, and then you get a GM times V pi. In this case, V pi is one half VID, and then you get RO internal system RC, you got R1 V1. So it's yeah, it's fairly simple, and you got a gain in this case, for example, is going to be AD is going to be it's going to be GM times RO in parallel with RC, and you can calculate GM by using IC over VT to get GM and so on. So this example is a little bit more complex because it did add resistance at the emitter. Again, forget about this one for small signal because of the DC current is open circuit. So current is going to flow this way, but it also added two resistance for the input. So this resistance represents the internal resistance of your sensor. Like if you got a sensor, pressure sensor, for example, and you measure the voltage, open circuit, you got a voltage. But if you short it, you'll find that there's a resistance. This resistance represents the internal resistance, and we split them into one half over here and one half here. And for this one, you can basically use the T model. And then let me see if I actually no. So basically, if the T model, you see that you got this one, and you have this. Basically, you have RE, you got RE, right? And then you have here, and then this is your input, and here you have. I draw the half circuit, so basically you can see that that's your input, one half. So if we want to draw the equivalent resistance, we can do that as well. In RO, we can draw that as well. But here, I think you don't have to. So you should look at here. You can find the voltage over here. And then you use this voltage minus this voltage, you get the current over here. So the only thing that you have to be careful is that the voltage over here is no longer the input voltage. There's a difference between the input voltage and the voltage at the base. So these two are actually different. But the other thing to be careful is that these resistance are not voltage dividers because the current are different. This is IP, this is IE. So if you want to write, you're going to write how the equations look like. It's going to be IB times RB plus IE times RE plus RE. So that's how you're going to write your input, right? And then on the other hand, you got VO1. You got VO1 is going to be your IC times RD, and which here you have a minus sign. And VO2, of course, on the other side has a positive side. Now, and then you get them too. So, and again, based on relation between IB, IC, and IE, you plug them in, you can cancel I, and you can get the actual expression. And then you take the ratio, you get the eventually you get the gain. And the gain equation is a little bit complicated in this case because you got RE, and then you got a let's call it RB. You got two resistors here, so it's a little bit complicated. So we're not gonna go too much details about how actually to calculate it, because we don't have the time. Here, we want to talk a little bit about the common mode what's differential mode input. So here, what we have is that we have VPN voltage plus small signal with VCM. And then we have our asset here. So this is very common. In amplifiers, you always get some sort of DC, and then on top of DC, you get some sort of AC. But you could also get you could also get a DC plus AC, but both are common mode. So this is what I want to say is common mode. Most of the time, it means some sort of DC voltage, like 1 volt on both sides, right? So that's clearly common mode. But what happens if I have input AC, same voltage, same frequency, same phase on both this side and this side? They are also considered common mode. So that's why here we have VCM capital DC and VCM lowercase. And then you could also have a differential input. So you might have three things merged all together. And then what we want to discuss here is that if the transistors are not exactly identical, like we saw how we said, oh, they're matched. But in process, you know that it's very difficult to make 100% identical transistors. So they could have like 1% difference. And also resistance. When you go on DGK, you buy your resistance. You know that you have to choose the precision is 1%, 2%, 5%. The higher the precision, the more expensive. The best you can get like 0.001%, which is could cost you like $1,000 each. But if you buy the 5% resistance, it costs you like 2 cents each, right? So so then if you buy 5% resistance, it is possible that these two are so good that they're actually identical. But if you're not so lucky, you could get actually their difference is 5%. Because this has 5%, right? So 5%. So if this is 5%, we're in a little bit of trouble because it's no longer symmetrical. The output is no longer going to be the same for even the common mode. It's going to get a slight output at both sides, and then we're going to have trouble to look at output. Let me see what I should do. More input. Yeah. So basically, this just explains that you have like here is we look at the capital VCM, which is common mode, and we look at common mode of small signal input. And if this circuit is identical, we know that the output is going to be 0. Well, not 0 at the terminal, but the VO is 0. So VOD is 0 in this case. But if you use a small signal model, then similarly to what we have done before, you can do voltage. You can do voltage ratio because you can calculate the voltage here. No, not this one. For MOSFET, there's no current here. So basically, you can use the current. If there's no current here, the ratio of current is the same on this one and that one. So your output is here, your input is here, and this is what your ground. So what do you think the gain is going to be? It's simply the ratio between the two resistors. It's output resistance and input resistance. It's very simple. So in this case, you look at the gain, it's simply going to be RD over 1 over GM. It's going to be RD times GM, and this is your A. So this is what we have all the way along, that we got this, the gain is RD times GM, for single one it's minus RD times GM, but now we observe the circuit, you got exactly what you want, because this is the current, and this is the resistance, and that's the resistance. Your voltage here is I times RD, and this voltage is I times 1 over GM. So simply, so that's how we get. But then, if you have this, so that's for the differential gain. Now for common mode means if this input and this input is the same, the current is not flowing this way, it's flowing down, flowing up, but actually they both flow down. If they both flow down, they flow through this RSS. So therefore, you cannot neglect it for common mode. So that's why we draw the half circuit with 2 RSS here, because this is RSS in parallel. So if you sub them, it's like a 2 in parallel give you 1, right? So that's why we have 2 RSS here. So this is half circuit, this is half circuit. And for this half circuit, without like you join the small signal circuit, can we identify the gain together? What do you think, the gain here? So let's call it what do we call it? Let's call it VCM. No VCM, ICM. What do you think? What do you think we can, if we can observe the gain over here? Yeah, similar if you look at the other circuit. Basically, if you draw the small signal circuit, what you have is instead of this one, but you have another one, 2 RSS over here. So the voltage here is this way, the voltage here is that way. So therefore, it's going to be RD over 1 over GM plus RSS, because the 1 over GM is very small, so often 2 RSS, 2 RSS. But actually, that's what you get Now, if you still have doubt, you can still start to write down like equivalent circuit over here. You got ICN equal to I times 1 over GN plus I times 2 times RSS, and you write VO equal to RD times I, right? Minus, right? So one side. So you write this down, and then we like this is VO1, like VO2. So you have both of them, and you have VO2 as well. So you have VO2 equal to minus RD times I, and you plug this in. And you got, and then you start to get the actual gain here. So this is the important equation for the common mode, because once we go to this point, you might say, okay, if RD are not symmetrical, which means if this and this are not the same, your gain is going to be so much different. So just for your information, again, we're gonna skip the BJT for common mode rejection ratio and so on. So what we have said before was VO1 if ACN equal to VO1 ICN equal to minus like RD over 2 RSS. So this is going to be the same ICN2. So therefore, your actually CM gain is going to be VO2 minus VO1 divided by VCN ICN, and that's going to be 0 because these two identicals you add one minus one, you get 0. So you get that. But if RD is different, which means if RD1, let's say, if RD, I don't know, if RD2 equal to RD plus delta R. So this is typical, like assume one of them has a volume, another one has a delta difference. You can probably to get your, instead of having the gain, maybe we can look at the actual voltage. So which means your voltage, VO1 is going to be same as RD times GN. Times divide by okay, let's do this. So we're going to have ACN1 equal to minus RD to RSS, and we have ACN2 equal to minus RD plus delta RD divided by 2 times RSS. Okay. So if you look at output, which means VCM1, it's going to be minus RD 2 times RSS times VCM1, VICM, and VCM2 equal to minus VCM or VO1. So VO1 and VO2 equal to minus RD over 2SS to RSS RD plus delta RD and times VIC. So you got this VO1 and VO2. Now then what we do is we use VO equal to VO2 minus VO1. And then you'll find that the way that I think I did it was opposite. If I do VO2, if I do RD1, this will be positive. So, but now what I did, I'm going to get negative sign, which is fine. We are interested in absolute value. So it's going to be delta RD over 2 RSS times VICM. So from here, we get the CM gain is VO divided by VICM. So we got third RD over 2 times RSS. I think I have a minus sign, but here I'm going to take the absolute value, which is going to be good. So, and then I can further write this down to be R third RD over 2 times RSS, which is equivalent to RD over 2 times RSS times third RD over RD. So what this means that, no, I think maybe I made a mistake somewhere. Let me see. Yeah, right. It's actually correct. So which means you do get a gain. So the larger the difference and the larger the common model gain. So you have a small signal input at the both sides. You think it's the same. You think output is 0. Actually, it's not. It has a little bit output. So if we use this, but this is going to be small. This gain is typically very small. So to evaluate how good this is, we actually define. We look at for AD, and if you remember AD, we have AD was previously already solved. We have AD was like GM and RD. So for this, so now we put this together as a ratio. We call them common mode rejection ratio, which is equal to AD over ACM. And of course, you can plug in all these numbers. I'll write down this equation. So it's going to be GM times 2 times RSS over third RD over RD. So this is what we call a CMRR. And you can see that the CMRR is related to this. If the third RD is very small, you'll see MR is very big. So if the third RD is 0, if this is 0, which is the denominator is 0, therefore your CMRR is infinity, which means this is good. So when you buy IC chip, it tells you the CMRR. The bigger the CMRR, the better the yeah, so this is typically in the thousands, like 5,000, 10,000, which is the good one. If you find one that only give you 100, that's a lousy chip. Okay. So yeah, so you guys are gonna expect this one on the quiz, you know, how to calculate CMRR. So we're gonna jump into our next part of our multi-stage. So this chapter has two fundamental components. One is the differential. The other one is multi-stage. The reason we need multi-stage because the gain is typically not large enough from what we want. So therefore, we want to increase the gain. That's one reason. Another reason is that for differential input, it does not have a ground. So this one is actually a differential input. It's not connected to earth ground. But eventually, when we make use of the output, we have to create a ground. Therefore, we have to convert this double-ended. Like this one is like here. This output is relative to each other. They're not relative to ground. You can take the output to one stage, again, you can take another stage, but eventually we have to convert them into a single-ended. Single-ended means one output, one ground. So we have to add another. So minimal, typically minimal is 2-stage, like one amplifier, one single-ended. Most popular one is the 3 to 4 stage. The 2 stages try to increase the gain, and one put a single-ended. Okay, and then 4th stage is more like a 2-stage gain, 1 stage single-ended, and 1 stage with the emitter follower like a buffer to increase the to reduce the output resistance, okay, so that you can use all the work you need. So this is why we need multi-stage. You can simply like put things together to get a multi-stage. It's very simple. But before we do the single multi-state, let me do two things. One is that let's look at how we convert a double-ended to a single-ended. So that's very important one. To connect a double-ended to a single-ended, the cheapest way or the easiest way is simply to ground for one like drain. You see here, if you remember for the differential amplifier, what we had was two input, we have two outputs, right? So we take output from between these two. But instead, we ground Q1, the drain on Q1. So now we only take output from the drain on Q2. So therefore, this becomes a single-ended. So this is the simplest way to do double-ended to single-ended conversion. But the problem with this one, we have a little bit of problem. The problem, of course, one is that we are using this resistance as a load, which is not optimal. And secondly, when we ground this one, this transistor will have a different like VDS. So they might have a slight different in terms of their operating status, even though they are both in saturation, but because of what it's different, right? So in order to balance this type of thing, so what we do is we use a current source load. So before I move on, you guys already know how to draw the equivalent circuit, right? So in this case, you can simply draw either T model or pi model. So for the pi model, for example, basically you have this input here, you have 1/2 input, and you have your drain. So you have your drain grounded, and on this side you have your current source, and you have resistance. Actually, you have this over here. But since the current actually going this way, so this current is actually negative. So you have VO is equal to GN times RD times 1/2. So this is your gain. So this is actually a third problem, is that if you do single-ended, your gain actually becomes half instead of 1, right? So half of the input. So this is something that we try to avoid as well. So that's why we want to move on to the next slide. Oh, here is a equivalent circuit. So instead, we use the current mirror load. So when we use the current mirror load, you know that all these transistors are going to be matched, especially in Q3 and Q4 are going to be matched. So when you have Q3 and Q4 matched, you know already Q3 is the reference current and Q4 is the load current, right? And then you have VG1 input over here, and you have VG2 output over here, and we take output VO relative to ground, and we don't take, because you cannot take output over here because this output is actually connected to the base of Q3, right? So this is like creating a virtual ground to take the output. So this, but this one has a couple of advantages. One advantage, we know that the load resistance RD is actually converted into a current mirror, right? So that's number one advantage. Number two advantage, if you look at the circuit, it's actually pretty much symmetrical, okay? And so this is good. The third advantage is that, well, maybe there's no third advantage. So the equivalent circuit of this one, if you draw the equivalent circuit, you can start to draw like this, going to be something like this on this side. And then on this side, you have, it's a small signal again. So this one, you look like this current source and here. And for this one, you actually connect this yeah, you can have the same like current source, and then you have like a resistance connected on this side as well. But then you have this drain is connected to the base. So therefore, basically, this one creates a virtual ground for you. Yeah, so we have this analysis in the next couple of slides. This one is looking at the DC biasing. Since the current all like identical, the transistors are matched. Therefore, you have 1/2 current in each branch. There's no current here. All right, so if we look at output here, OVO is VDD minus VSG3, which is this is VDD is over here minus VGS3. So which means VSG3 here. So this voltage minus the voltage, we get this output. So this is for DC. This is DC bias. For small signal, it's a little bit different story. For small signal, we go through this is for common mode. See, for common mode, each of them is going to have the same voltage. So therefore, you're going to have the same current, identical current. And therefore, you will have 2 times current going to that. You probably know already, this goes back to what we just discussed a few minutes ago. And you can actually calculate the gain. But when the things are matched, your output is actually 0. Because from here, you can see why. Because the current here is the same as this current, and therefore there's no current this way. So you have basically 0 output. That's for the common mode. And for differential mode, we're going to apply half voltage over here and a negative half voltage over here. And you get output over here, which means your current is flowing all this way. So therefore, we can get VO over here, but you see the difference over here. This is 2I. This is the most important part to understand for this current mirror. You know, earlier, I said the output for this one, the gain is going to be doubled. Remember the other one with RD with simple idea, the gain reduced by half. But for this one, your gain is going to be going back to the original gain or double-ended. Why? Because the current. If you look at the current, when you have an input over here, you create a current I in this branch. You create a current I. Now, if you create a current I in this Q1, this current is going to flow in Q3. So Q3 is going to have the same current as I. But what happened with Q3 and Q4? Their drain and the gate are connected, which means they're going to share the same VGS. If they share the same VGS, means they will share the same current. So this is like a current mirror, but now we're talking about small signal mirroring. Small signal, which means Q4 is going to have a current of I. So Q4 is going to have a current of I. So if Q4 is current I, and this I is going this way, and Q4 is Y, so this is 2 times I. Okay? So you have 2 times the current, you have 7 load resistance, what do you get? You get double the gain. So that's the beauty of this current mirror load, how to convert it. Yeah, so this talks about how to calculate the equivalent circuit and how to calculate the RO of the differential pair and stuff like that. Maybe I should just do a little bit of illustration here to see what kind of gain we're going to get for this circuit. So for small signal, if we look at the equivalent circuit, basically we're talking about resistance in parallel, resistance in parallel, resistance in parallel, and this resistance in parallel. And if we apply a voltage over here, we can find our output resistance. If you apply voltage here, you find current over here, you can find your resistance. Well, if you look at here, now if this is too complicated, you can draw the small signal equivalent circuit. That will make it easy. So if we draw the small signal equivalent circuit, we can do maybe we should draw like a one just to illustrate how this works. So let's start with Q1. So Q1 is going to be like this. This is all Q1. Now, you notice what happened with Q1 with a gate. When we look for the output resistance, we basically ground the input, right? So that's why this is ground. If this is ground, means here is a ground. So if this is ground, what do you have VGS? So VGS 0. If VGS 0 and this is VGS comes GM, what do you get here? 0. So this is actually an open circuit. So this is open circuit. Okay. Okay. And you can draw Q2 as well. So Q2 and same thing. Q2 is grounded. So this one is again an open circuit. Okay. So and then we connect over here, and over here we apply this voltage. And similarly, it's here. So now this two, of course, you can still draw the small signal model, but then the DC current is actually going to be 0 anyway. So therefore, you can only small signals. So when you apply voltage over here, and the current goes up and goes down, right? And see, this is what I'm talking about. The current going down this way, the current going up that way, and then it goes this way, and it goes up that way, and that goes ground, and then all the way from here, and all the way goes to the ground. So basically, you have RO2 and RO4 basically are going to be in parallel. So we actually get this RO eventually is going to be RO2 in parallel with RO4. And then if you want to find the gain, we know that the gain is going to be GM times RO. That's going to be like GM times RO2 times RO4. That's RO2. That's RO4. And so this is going to be give you the actual gain of the circuit. So from deriving the resistance and finding the output resistance, and you got actually the gain. So the gain now, if you look at the gain, actually, if RO1, if RO2 equal to RO4, and then you have A is equal to 1/2 GM times RO2. So this is going to be the what we call a intrinsic gain. So the GM times RO4 or GM times RO2 is the intrinsic gain of this transistor. But now you have load over here. This two becomes parallel, so you reduce that by 1/2. Therefore, you get a gain only 1/2 of the intrinsic. So this is the intrinsic gain, and this is actual gain. So with converting a differential amplifier into a single-ended, if we recall, the simplest way is ground one drain, but you reduce the output by 1/2, right? If we convert them into with the current load, and then all gain actually again goes back to the original volume. So the next, so with that in mind, we can go ahead to design a multi-stage amplifier. Do you guys want to continue? Then we'll finish early. Is that okay? Huh? Oh, do you, well, like we can probably. I don't actually feel comfortable today. I have a lot of palpitations in my heart. But no, yeah, no, actually, well, we want to go through these two examples, and we can. Okay, yeah, we'll probably can. So these two examples are very important. Again, these two examples are going to be our quizzes, but if you actually go to the textbook, it's very long. It's very long. So you're not going to spend that much of time in the quiz to do them. But the idea is that you need to understand the process of getting this done. And I'm going to give you like a preconditions. If you know the process, you apply the conditions, you'll get the answers fairly quickly, because they have multiple choices again. So in this diagram, what we need to do is the first step is to identify which is amplifier, which is a current source, and which is a oh, sorry. And which is a current source or current mirror, and which is like a stage 1, which is stage 2. So this is very important, and in the beginning, often it's very difficult for students to identify because there are too many transistors and don't know where to start. So for this example, if we look at it, we can look like you can always look from left to right and start to identify, and then you can write down which one is which. Okay, so we start from this side. You can see that this is our reference, which means this is already some sort of current source generated, right? So here they basically already. So there's a bunch of circuit over here. We don't care because it's already provided with a constant current. So if this is the constant current, if you look up Q8 and Q5, and what happened? So yeah, so Q8 and Q5, they're the gate and drain are connected. So which means the Q8 is a current source, and in Q5 a current mirror. And you go all the way down that side, you see Q7. What happened to Q7? Q7 gate is connected to gate of Q8, which means they all share the same VDS, right? So therefore, or VGS. So therefore, Q7 is also current mirror. So sometimes the current mirror itself is not accurate if this transistor are not matched. If they're matched, you can call it current mirror. If they're not matched, you can call them current source or current steering. Like this can be say 100 microamps, and this can be 200 if this double the area, right? But if we have some area, this is 100, and this is 100, and you can 100. Okay, so we found, okay, so Q8, Q5, Q7, they're current mirrors. Okay, you have done a good job up to this point. And next, we come down to Q1, Q2. Well, you look at Q1, Q2, what they mark? Minus sign, plus sign, and the gate. The gate is not connected to voltage, they're not grounded, and they're not connected to their drain, which means they are amplifiers. And you have minus sign here, plus sign here means this two is actually a pair of differential amplifier, because you get input like on both sides, right? Okay, and then we move down here with Q3 and Q4. Well, Q3 has the drain connected to the gate, which means this is the current reference, a current source, and this Q4 becomes a current mirror, right? Okay. So which means because this is amplifier and this is at the like a drain. So what do you call this two? Think about what we had from the previous slide. This is kind of mirror load. Now the reason why is this at bottom? The other example was at the top because the other one is NMOS, but this is PMOS. Look, this is a PMOS. Okay, so PMOS loaded at the drain. So this is your load, and the top one is actually the top one is actually the current mirror, which is the biasing current. So the top one provides the biasing current, and the bottom provides the load. Okay, so we finished almost only one left, and then Q6. What does Q6 do? Well, in this case, in fact, this is dual entity input, different input. By this point, we use the current mirror to convert that already into a single entity output. So the output is over here. Output over here, and the output goes to another transistor, which means this is going to be amplified because our input is connected to the gate, right? So this is the ground. Well, I mean, for AC, it's the ground. So therefore, this, what do you call this one? What kind of amplifier do you have? a common source, right? A common source. Because the source is grounded. So the common source amplifier is okay, but its output resistance is pretty high. So therefore, sometimes we would add another stage to become like a emitter follower, or source follower to become another stage, right? So this one here, and we do have a capacity here. So for now, actually, you can forget about this one, because this one is like a feedback. They take output over here, and it binds over here. But for now, we don't consider this one at this point. Because you can just consider it as an open circuit. Yeah, so that's fine. But later on, when we do the feedback control, we're gonna see, yeah, the actual feedback. It helps to stabilize the gain. But for now, we can forget about this one. So once you identify each of the stages, the key would be like first step, calculate the current. And this current is given. So therefore, these two currents, each are going to be half. Okay, remember, this is important. And I see many students made a mistake because they forget to divide this I by 2 when they calculate the common mode range. Right? So this I is half on each of the transistor. So and then you can take this circuit out to draw like, okay, so if we take this whole circuit, including this load, we go back to what? We go back to this, or we go back to like, yeah, this one here, right? So this with small signal we got basically here. So we have found this one, so therefore we got this one. You found basically the gain was single-ended. So we can take the input over here. We can call it like a V. Maybe we can call this like a V01, and this is half VID, and this is plus half. So we have these two inputs, and we got V01. Now, once you want V01, of course, this final stage is very simple. It's a common source. It's common source. So the final stage. So you get really the gain. So this is a common source. Now, for example, how do you write the gain of common source? The gain of common source, that's called common source, is going to be like minus Gn times R. Well, in this case, the top one is a current load, right? So therefore, you have resistance of Q7. So basically, this is just R07. Let's call this. Let's call this A02. It's Gm times R07. And then for this one here, you can get the gain to be A01 is going to be Gn times R04 in parallel with R05. Right? So and your total gain is going to be A01 times Y02, and you just simply put them together, you get your final gain. So and then you can go further to calculate the output resistance of this one, which is going to be just R07. That's output resistance. And input resistance, of course, is infinity because it's a MOSFET. There's no input resistance, right? So when you break this down, you find, well, it's fairly simple. I mean, not much, right? But then why is the book has such a long like a calculation to get to the point? If I show you, I think you guys have not many have a hard work. We get a 1 page here and 1 page here. Well, the reason because the book was asking you to calculate not just the gain. So they give you the current, right? So then they give you a current, and from current, you can calculate so they give you current. So ID is given. So ID is 1/2 I reference on this one, on the other graph, right? So, and you know ID is equal to 1/2 K times WL and then times VOV squared. So from here, you can start to calculate like VOV or WOL. Like if one of them is given, you can calculate the other one. So you have like 8 transistors. So therefore you have 8 different values to calculate. The WOL is given, that was a table, right? So give WOL is given, K is given, therefore you can calculate VOV of each transistor. So that's how you can calculate. And of course, yeah, so if you look at the WOL, it's actually pretty much different for many of them. So when I said this is when this is a match, it's much easier to calculate because everything is the same. But when they're not matched, you basically have to calculate the current over here. So this is proportional to this current over here, but by a ratio of W5 over W8. And then you divide by 2, you get each of this current. Okay, and then use that equation on the next page. You get the you get the VOV for each single transistor of the circuit. So that's why there's a table over here. So once you get VOV, and you can calculate GM, and we know that GM is 2 times ID over times VOV. Now, if you look at the book, they use VOV with a absolute value because we have PMOS and NMOS. NMOS is always a positive, PMOS is always a negative. But calculate the gain, we simply take the absolute value. So now you got GM of each transistor. So now you put this on the table in the second row, you get that. And then we have R. You got RO of each one. So we calculate RO at VA over ID, right? The VA, again, absolute value over ID. And ID, again, ID is different for each transistor. So therefore, you have to plug in each one of them to get RO. And then once you get RO, right, so that's pretty much it. So therefore, that's how you get a table like this. And so this is Q1 and Q2 and all the way to Q8, right? So, and then we start by calculating current ID, and we start to calculate by VOV, and then we calculate GM, and then we calculate RO, right? So that's how the table is like, oh, so many calculations, because you start by calculating ID for each one, and then you start calculating WOL, VOV, and you find GM, and you find RO for each one. You have the value for each transistor. So once you get all of that, you finally get the gain, and the gain that I already wrote it here. So basically, you have RO1, and actually, no, this RO7 is going to be RO6 in parallel. Sorry, please correct this one. It's going to be R6 because this Q6 has its own internal resistance, and Q7 also. So those resistors are going to be in parallel. You have 2 resistors. The GM, again, this GM is not simply GM, but GM6, right? So GM6, and this is going to be GM2. So and then you put them together, you get A. So and then you get A. Yeah, so you get A, and then you get a A1, A2. Then you get this. You get this gain. So if you look at, I just want to give you some value. So the gain of the first stage, A01 is 25, and A02 is minus 25, and you put together. $625. So that's your gain. That's the voltage gain. So and then it has a unit of volts over volt. So that's really, I mean, once you get to the point, I mean, you know the procedure. It's fairly simple. It's just tedious. It's just tedious to do all the calculations. Right. So as I said, I wouldn't ask you to find everything in the table, but probably typical values. Each of these questions, and of course, I will make sure they're not actually related to each other. But anyway, so but calculating the gain, calculating each of this value again, you guys need to really know the procedures how to get one from another. So, okay, So this is a multi-stage, but if you look at the multi-stage here, we do have a, okay, actually, this is minus, I'm sorry. So this is minus actually 625. Minus 625. Volt total, okay. So this two stage, as you can see, it has a little problem, right? Even though the gain was significantly increased, like from 25 to 625, but the gain is negative. So the gain is negative has a problem in many applications because we don't want some sort of negative output and it's hard to use. So that's why in the next example, actually you have to flip the gain in order to get your positive. So let me see. So this is a very old technology, it's a four-stage amplifier. And if you look at the circuit, it's not an optimum design because we've been saying that resistance is not good, not good. But in this circuit, we got actually 5, 6, 7 resistance, which is not good. But yeah, this was how integrated circuit started, right? So and it works. So people still use it. So we can, again, for doing this, you need to understand the process, the procedures, how to identify the function of each transistor. So let's go from left hand to the right hand. We identify one by one. Okay. So let's start from here. So if you look at Q1, Q2, what do you see? You have the base marked as input, right? And you have them back to back. And then you have also, you look at output, you have this kind of output. So therefore, this is your differential amplifier. And since your input is over here, so that's your stage 1. And then we go down. What do you see over here? See here? This base is connected to collector, which means this is a current source. And the current source is determined by the current over here. And the current over here can be calculated because this is minus 0.7, right? And you get a minus 15 plus 0.7 to 14.3. 14.3 here. So 14.3 minus 14.3, 0 minus 14.3 divided by 26.8, you got 0.5 million. So this current is 0.5 million. And their base are all connected, which means this is the current source and this is the current source. If they're matched, you will get the same current. But if they're not matched, we have to calculate by multiplying the area, the ratio of area of this one, that one. Once you find the current over here, you will see that each of this will get half of the current. Oh, that's important. Again, this is important because some students got the current over here, got the current over here, and then they apply the same current on this, which is not correct. You get really hard. Okay. And then we move down to this side. We see easily Q6 is connected to Q3 and Q9. So therefore, this is a current source. But you see here, 4x. The market here 4x means this is 4 times bigger than this. What it means that the current over here is going to be 4 times the current over here. So the current over these two are going to be 4 times. So we're down here, now we come up here. So we mark this one. So especially you guys understand this number 4 and this. And then we move up to after Q1 and Q2, you see the output of Q1 is connected to Q4. The output of Q2 is connected to Q5, which means this one is going to be a pair of differential amplifier. It's a differential amplifier, right? It's because it got 2 inputs not from ground. And where's the output? The output apparently is here, right? So this is stage 2. Stage 2. And for stage 2, you got output going to Q7. But look at what happened in Q4. Q4 is directly connected to the voltage, which means for AC, that's a ground. So which means we have grounded Q4, which means we have converted dual ended output or dual ended input to a single ended output. We converted already. So now you know we converted, right? So you look at a few slides back, how we converted, and let me just remind you how this is done so that you get a better understanding. Not here. So we basically ground one. This is BJT, this is MOSFET, the other BJT, which is again same thing. So we ground this one, and we have this output over here. So, okay. So now we got stage 2. And what type of amplifier do you have in stage 2? I mean, it's a differential amplifier, that's for sure. But is it a common source or the common drain? What do you see? No. It's a BJT, and you have a current source, which is a DC current. For AC, this is open. So you have this full actually connected with the virtual ground over here. So which means this is a common emitter. It's a common emitter. Okay, it's very simple. For common emitter, easy to get the output. Okay, so that's stage 2. And output of stage 2 is connected to where? To the gate of Q, the base of Q7. So this your stage 3. And your stage 3 has an input connected to the base, and then you have your emitter connected to ground by similar resistance, and you have your drain also connected to resistance. But your output is as a drain. So what type of amplifier do you have on this one? Is it common drain, common source? I mean, common emitter? Well, you see, your output is as a drain. So it cannot be a common drain, right? But it's not a common emitter, right? Because you do have a resistance as an emitter. That's a PMOS, right? So that's your emitter. So this is what we call a common emitter amplifier with a resistance at the emitter. Remember we talked many times in the beginning today? We have RE lowercase and we have capital RE connect at the bottom. So this is what you have. So this is a common emitter amplifier with a resistance at the emitter. So this is what you have over there. Okay, and the output is at the grid of Q7. The output is connected to Q8. And then the final output is over here. So which means this is your stage 4. Okay. So now can you guys tell me what kind of amplifier do you have for the last stage? Common collector? So the collector is coming to where? Ground, AC. So ground means common collector. This is common collector. Common collector is also called emitter follower. So you know that the gain of this thing is approximately 1, and the output resistance is very big. That's why in chapter 7, we spent a lot of time, and in chapter 8 too, we tried to derive the output resistance and the gain of a common emitter. Yeah, you had a question. The collector connects to 15 volts. That's a DC, but for AC, that's a ground. So we have 4 stages. So now what you need to do, of course, to do this type of problem, the first step is to find the current or DC biasing for each one, the voltage, the current, you can do it. And it's not that difficult. You start by looking at this one, you find the current over here, right? And you find the current here, we find the current over here, then find the current of each one. And this 4 times, so you find the current of each one of them. And once you know current, voltage minus voltage drop, you got DC voltage over here, DC voltage over here. And this current is known, and voltage minus voltage drop, you get voltage over here. And this one too, you have basically you have on this one, okay, so you have 0.7 volt drop over here. And here you have 0.7 volt drop over here, right? So then this minus 15. And then basically this is minus 15. And you find the difference. So this is your output DC voltage. If you know the current over here, we don't actually know. We know the current over here. We don't know the current over here. We should be able to find the voltage, the DC biasing voltage at each of this one. 15. And then I don't know over here. -7. So yeah, basically we should be able to do a loop because this is -15, right? So and this two is 0.7. So this -15, -15, and -0.7, and then we should be able to find actual current over here. So actually, if you look at the results, is that we have so you see here we got 0.5, 0.5, 0.25, and we have 13.3, and this is Chicago's, and then this is 1 milliamp, this is 2 milliamp, this is 1, and we got what here as 12, right? And then over here we have so okay, so we have 12 over here, so this is 0.7, so therefore we have 12.7 at this point, and we have 15 minus 12.7, we got the current over here, so that's 1 milliamp. So once we got 1 milliamp, okay, so we find the voltage drop over here. So this is minus 15, plus 15.7, so we got 0.7 here. 0.7 here, this is 0.7, we got 0 here. And then this is minus 15, 0 minus 15 divided by 3, we got 5 milliamps. So that's how we go step by step, always come to this point. So this is all DC biasing. After the DC biasing, we would simply start with by looking at each of the stages. So stage 1, we have input Q1, Q2, and we basically get rid of DC biasing current. And you can see that you have 2 loads. But the only thing we have to be careful is that if there's no second stage, we will get the gain directly by GM times R2. We get the gain. But with the load on the second stage, we have to find the input resistance on the second stage. So we put that resistance over here to find the voltage. So therefore, the first step is to find RI2. To find RR2, and then you need to look at the second stage, right? So the second stage, you need to draw the small signal equivalent circuit, and you'll find one HSR pi, which is second stage input resistance. And you would go back to put this in the first stage, you find the gain on the first stage. And the second stage, same thing. If we don't have a load, we'll get the gain fairly easily. GM5 has R3, but since we have load at the third stage, we have to find the input resistance RI3. Okay, so to find R3, we have to draw the circuit of I3 and then to look for the small signal equivalent circuit and then find RI3, and then we have to find RI4, to calculate the gain of this stage, and this is the last stage, right? So then this is what last stage. Well, this is the common the emitter follower where you can find the input resistance of this one, which is very big volume. And then eventually we'll find the gain of each of these stages. So the way to calculate this, the book actually has a very detailed steps, like one by one and going through. I think I'm not gonna really go through the steps, but I just want to explain what happened. So, and then the book says, well, instead of drawing the small signal circuit, instead we can draw the current relations. When we draw the current relations, basically what we're doing is we neglect current in the base. So what we're doing is assume the bed is quite large, which is kind of true. It will create a 1% error, so which is acceptable at times. So if we assume the base current is 0, well, this is actually not exactly true. What they're saying is that when you go from base to electric current, use a better current, right? But then when you like look at the emitter current, we neglect IB of the input. That's what it is. So in this circuit, this started to show the current relation. So if this current coming to the base is I, and the current for IC will be better times IR. So IC1 and I is the same. So this current going like looking this case, IC1 going down, IC2 going up. So IC1 is better times IR. And then this IC2 going up, going this branch, and then you go to IB5 that comes this way, and IC going like this way. So the current coming this way, and it goes this way, it comes this way. So this IC5 is better than IB5. And then you have here, you have IB7, because this is the PMOS, you got IB7 coming out, and this IC7 is IB7 times better than IC4. And then you have IB8 going this way, and this IC8 is better than IB8. So if you can find each IC, you'll be able to find the actual current of IC8. And once you find IC8, multiply by R6, you get VO. And you use VO divide by VID, and you get the whole gain. So this process was done, and actually it is quite interesting to watch, and then you can find the gain. I'm not gonna write it because it's very complex. Unless you read it, you will have a hard time to really understand what it is. So I think what we are covering today is we basically finished chapter 9. So again, going back, for next week for quiz, for example, we start talking about the CMRR, which is very important. And then we talk about the single-ended, that's important. And then we talk about this two-stage, how to calculate the VOV and all this equation, important. And then for the final one is to identify the stages, or maybe even to calculate the current in some of these transistors, how to do it. And then find the stage. I don't expect you to, I wouldn't put the whole problem on the quiz because it's impossible. Even I do that, it will take me 45 minutes to finish it. Okay, so it's impossible. But looking through and understanding what type of amplifier, that's critical. Like, again, we go back to repeat, we find this is the current source, and this is the current source 4 times of that, and we find that this is a common emitter amplifier and differential, and this again another common emitter amplifier is single-ended, and this one is a common emitter amplifier by resistance at the source. I mean at the emitter, and this finally is the emitter for the water, right? So if I give you say the gain of each stage, you should be able to find the total gain. So if I give you certain value, if I give you say the output resistance, and I want you to find the voltage output, right? So you should be able to find it if you know the input. I give you the input, say 1 milliwatt, and you have all the gains. And I say, okay, so I give you the gain of each stage. You should be able to find the gain, the total gain, and the voltage. And you know the resistance, you should be able to find the output current over here. So kind of the small signal current, not the DC current, because the DC current already we found the other stage, right? So when you guys look at this, there are two things here. So one is the DC biasing calculations, other one is the small signal. So don't confuse the small signal and the DC biasing circuit. So when you, for example, one of the students asks you, is this a DC voltage? Yeah, actually it is a DC voltage, but for small signal, this is ground. So that's kind of how to distinguish. So when I want to calculate the small signal current at the final branch, I wanted the small signal current, not the 5 milliamps. The 5 milliamps is a DC current, is a biasing current. But if I give you, say, having an example, let's say it's 1 millivolt and the gain is 1000. 1 millivolt AC. Now how much voltage do you get here? The total gain is 1000. Huh? How many volts? Input is 1 millivolts, and gain is 1000. 1 volt, right? You get 1 volt, and you got 3 kilo, which means your output current over here is going to be 1 volt divided by 3. It's going to be like a 0.3 3 millivolts, milliamps. But your DC biasing 5, so your actually current is on top of that 5 DC. So if you look at it on the oscilloscope, you're going to see something here. So this is your 1 volt, and you have 0.33. So that's what this is what it's going to look like. So that sort of sense, eventually want to be able to really very quickly to get to, instead of have to think about, oh, what is it, what is that, things like that. It's going to be very difficult, right? So with that, any questions? No. Okay. No. Yes, sure. Go ahead. The CMR. Yeah.
EMR.
Yeah. The common mode rejection. And so we basically skip the DC offset in the book. So again, you guys want to read it, but it's similar to the CMR, how you calculate. Because when you have input, basically difference, when the transistor is different, actually the output is not going to be identical. It has slight difference, like a couple millivolts of DC offset, right? So we skip that part. But I think we pretty much covered this chapter well. You guys should be able to, understand. Again, going through murals, going through the differential, going through multi-stage CMR, and also common mode range that we tested today. So, and then moving on next week, we're going to start to talk about the frequency response, and then we talk about later on, talk about feedback. So it's all add up. So if you like, I think in the beginning, what I wanted to let me go to one of the circuit over here. Like if you look at this circuit, I mean, if you look at this half circuit, we got this already covered in chapter 8. So this really no surprise. And if you look at one of the circuit we started today, here, like here, or this one. I mean, when you stop at this one, I mean, you got a half circuit, and this is something. This is one like or stage 3 in this fourth stage. You got common emitter with a resistance as an emitter. That's what it is, right? So whether it's a differential input or single input, the principle is same, basically the same, right? Now this one here, let me see. Okay, I wanted to show you one of the circuits that I talked about. No, not this one. This one here. Right. Basically, you look at this circuit, right? This will end, right? And then this is the T model that we have. And getting from this one to this one is a little bit difficult if you forgot already what you learned in 330, right? So that's how we spend time to go from there to there. But once you get this point, we're able to basically find the gain easily from the circuit. We don't even have to do further derivations, and just by observation, you can get the gain. Right? Okay. Anything else? Okay, no, then I'll see you next week. And for Friday, if you guys need to office hours, we're going to I'll be on Zoom. So if you want to don't want to come in person, you want to have a question, you can always log into it. Okay. And the link was posted already. Okay. Guys, take care. Thanks.
So new. So new.